This clip is from just one of the many recent Senate inquiries, and while it concerns the banking sector, it does raise similar questions for our own industry. While we could all answer any questions about our recent processes, what about ones from 10 or 20 years ago? As employees come and go, the knowledge required to carry out these tasks is gradually lost. And while some of these processes are documented, they at best capture the key steps of a task, rarely providing insight into the decisions taken. In this way, we keep the end results, but store the knowledge and expertise needed for replication separately, if at all. Open spatial analytics aims to address this, using scientific workflows to integrate data, documentation, and expertise in a way that puts science at the center. But what are scientific workflows? Scientific workflows share much in common with business workflows, in that they are tools that allow us to break down our tasks into manageable parts using the metaphor of flowcharts. There are dozens of scientific workflow platforms available, and after a thorough investigation, we found that 9 best met our project's aims. This was primarily due to it being open source, cross-platform, and easy to develop for. In this example workflow, squares represent processes applied to the data, and arrows represent the flow of data. Here, we perform a variety of spatial operations, saving all of the configuration options so that the entire process can be replicated again at a later date. In this way, scientific workflows allow us to capture the expert knowledge from the user by providing a visual language for self-documenting analytics. Here we can see an example of building workflow in KNIME using some of our geospatial nodes. We first take a look at our data using the map view. We then add our buffer node and connect it up to our data. We also then add a distance to the buffer by connecting it up to the lower node. We can then open our map view to see the output of this operation. Our next example shows the completed workflow, which we will simplify using metanodes. Metanodes allow us to collapse collections of nodes into single boxes for clarity. To do this, simply select the set of nodes you will be collapsing and then select Collapse into Metanode. After we finish, we tidy up the workflow by clicking the Auto Layout button. To look inside a metanode, simply click on it. If we can store all of our processes, then we can also share them. To do so is simple as exporting them. The intermediate data at each node is also available, meaning that everything required to generate the final data is present. Once a workflow has been sent to someone else, they may want to run the analysis with their own data. To do this, simply point the import nodes to your new data. As you can see from the map, we are now performing our analysis for the whole of Victoria. We now do the same thing for the other 3 data sources, then run our analysis again. When we open our output map, we can see that the analysis has found a few places of suitable land near the coast. A key feature of scientific workflows is their ability to integrate a wide variety of tools. Here we replace some of our data with a connection to a PostGIS database. Instead of using a filter, we use an SQL query, which as you can see here produces the same result. We then connect these nodes up to the rest of our workflow and rerun it to produce our output. We have also integrated similar nodes for the systems listed here. To demonstrate the power of scientific workflows, we are replicating Geoscience Australia's procedure for constructing the national DEM. This involves blending over 100 terabytes of LiDAR data from over 60 different surveys together into a coherent whole. GA's process is well documented, but this information lies separate from the source data and tools used. Simply re-implementing this process would not show what was actually done, but by capturing it in a workflow, we can create a record of its provenance. Here we see the case study broken into a workflow. It's further broken into 2 stages, data conversion and data manipulation. For the first part, we resample the tiles into a lower resolution. Then we merge the tiles into individual surveys. We then generate polygons from these surveys, and finally reproject these surveys into the designed reference frame. The next stage is the manipulation stage. First, we find out where the surveys overlap. We then calculate the height differences in the overlap, determine where to start and end our cut lines, calculate the path between these points as the lowest overall difference, clip the boundary polygons with these lines, and use them to clip the surface rasters. Finally, we merge all of the rasters into a single DEM. This is what the process actually looks like in KNIME. While it is more complicated, it can be streamlined using metanodes. Currently, it takes 15 minutes to process the data in our test area. Fortunately, our process can be easily broken into parallel tasks, which allows us to massively reduce our runtime through cloud computing. And analytics are not the only parts of an organization's processes. This is why our workflows aim to be integrated as parts of a larger business workflow. In this way, we can capture the entire process from start to finish, all with a completely reproducible and auditable chain of provenance. We also aim to improve our user interface, making it easier for users without spatial expertise to manipulate spatial data. Moving forward, we foresee users asking questions about spatial data rather than simply performing operations. Thank you for listening. Are there any questions?